Okay, so modeling tips and tricks with GSA. Now, before we start, let's have a quick show of hands to see how long people have been using GSA for. You should see a poll on your screen there. And okay, a few votes coming in. Just and excellent. Let's have a look at that. Well, quite a spread, ranging from never to long-term users. Alright, so let's hopefully we'll have something for everybody in here. So, first thing to remember about GSA modeling, in fact any finite element analysis model, is keep it simple. It's very difficult. It's very easy to make something difficult and very difficult to make something easy. Always the trick with the GSA model is to make it as simple as possible but not oversimplified. Otherwise you'll sort of lose on accuracy. It's just a matter of judgment and experience, and something to experiment with. So, general modelling first of all. The main thing to talk about general modelling is axes. I think everyone's familiar with the fact that GSA has Cartesian coordinates. I suppose even those who haven't used GSA before. GSA defaults to using Cartesian coordinates, standard X, Y and Z coordinate systems, but it also has cylindrical and spherical coordinate systems, or AXI sets, available in there, which, if you're dealing with cylindrical or spherical structures, surprise enough, can be very useful. So let's have a quick look at that. First of all, let's go that. This I've got just GSA running. I'm going to start a new model. Now, axes. You find the AXI sets down underneath the geometry section, and there are a few AXI sets in there. If I go to graphical view and switch on my snap grid, you'll see in the current grid, yeah, there is a global grid, global Cartesian X, Y and Z coordinate system. There's also an X elevation grid, a Y elevation grid, and a global cylindrical grid. And if I just go to an isometric, this will show it better. So let's just change that to X elevation, and you see elevation in the X direction, Y direction, and the global cylindrical. There isn't a global spherical, but we can soon create that. I'm sorry, it's difficult to show here. But to create these AXI sets, geometry, let's just use the wizard so it's slightly clearer what we're looking at. You can create an axis which is defined by the origin point. So this is a point in space. The next is a vector. It's not a point, it's a direction away from that origin point, and this is the direction of the x-axis, or the direction of the zero rotation if you're looking at a spherical or cylindrical axis. And then the third axis is, direction isn't quite so important, but this one defines the plane of the xy grid. So the length of these two vectors doesn't really matter. The direction of the second vector is crucial. The direction of the third vector just has to be sufficient to define that plane. If we define the coordinates, let's say it's going to start at 220, and then these will be the directions, and I'll say it's going to be cylindrical axis, and I'll call it my axis. And I'll switch on under labels the axis set. So you can see there's the global cylindrical, there is the my axis set, and if I just change the current grid to being a new grid, which is based on, not that one, my axis, and you see the snap grid is based on this, but also if we look at the nodal coordinates, is also based on the radius, angle and elevation, which is different to the global cylindrical and global axis. And if I just set something 0, 0, 0, go back here and set the current grid back to the global grid, you'll see that the nodal coordinates update accordingly. Now if I just set that back to my grid, and what I'm going to do is I'm just going to draw in an element in there at the moment, and you see the coordinates gone in. And the thing about the these axis sets is they can also be used as part of things like the move and copy command. So for example, I can set my axis to use a particular axis. Let's use my axis, and I'm going to copy that element. I'm going to copy it round by a rotation angle of 30 degrees. But similarly, I can also move things. So if I select these nodes, I use the move copy command, I'm going to move those nodes. Now note these are drop down lists. These are drop down, so I can say I'm going to move not by a value but to a value, and set those all to 0, and it sets the rotation value of those nodes all simultaneously. This can be useful. So 1D elements. 1D elements often sort of a mainstay of many of the GSA models. Now these GSA 1D elements have their own axis set. See, there's and the local x-axis is defined from the first node to the second node in the beam element definition. I say beam. We have many 1D elements: beams, bars, struts, ties, springs, links, but the basic principle is they're defined by 2 points. Now the x-axis is along between those 2 points. The z-axis is then the most is the perpendicular to the x, which is as vertical as possible, meaning that your web of your I-beams will always be vertical. Mathematically speaking, it's the perpendicular to the x which has the maximum z component. Now once you have these two axes, then the y-axis is just the right angle to those two. Now because the local z is as vertical as possible, if your beam element is vertical, you've got a column, there is no vertical component to the perpendicular to the x. The x is vertical, which means that previous rule cannot work, and a new rule kicks in, which says that for vertical elements, the local y is parallel to the global y, and then the z is then the vector direction left over from that. If you look at the solids and you see your sections are sort of, your columns are sort of spinning around a bit and so on, which can often happen in the CAD import, especially if the model is a long away from the origin, then the columns are not quite vertical and things just need to be straightened up. Also, of course, other option is you can adjust the verticality tolerance in your preferences, which defaults I think to 2 degrees, but you might want to make that larger if necessary. Now you might see on the diagrams there mentioned about rotation. Now rotations of elements can be set by two methods: the orientation angle and the orientation node. Here are 4 beams with no orientation at all, and here we've set a 90-degree angle onto those. Now I think most people are familiar with that, but there's another method which is orientation by node, and that you just specify a node for all those beams to be orientated by, and in this case the local y-axis then points through that nodal point. Okay, very useful for circular structures, but also sloping structures as well. You can combine these two together, so this is a combination of the 90-degree angle going through a node, which means now all the z-axes line up with the that nodal point. So 1D elements in operation. Let me get to that and start a new model. What I'm going to do is I'm just going to build a staircase. Now this the way to do build a model, there is a number of methods. There is the old-fashioned way for DOTs, which is the direct table entry. And here you can just type values into the table, and if you type values in, it takes them. If you just hit enter, it copies the information down from the default, and you can see there are my 2 nodes there, and then I can then say I can select a beam element which goes from node 1 to node 2, and there we have the definition. Now this can be quite good if you're copying model information to and from Excel or similar type methods, or if you want to fine control and get in and adjust things, but most of the time the sculpt menus on the sculpt toolbar are very useful. So let's create another beam over here. But this time what I'll do is I'll copy it. So the move copy command, I'm going to copy that beam, global Cartesian coordinate system, 1 meter in the y direction. And you see the y direction there. Preview. It's just off screen. And you can create it once, copy it around. Again, this can be slightly there are other options. There is the add element sculpt tool if you've got nodes already. I can snap on one node, snap on another node, and it draws the elements in. You can also create elements by, well, unless we can snap to the node. It's also wanted to snap to the beams as well. Now by default, if I right click there, we see snap to the center of the beams, and snapping the center of beams breaks that beam there and adding a node in. If in hand we want to snap to, let's say we want to snap to the perpendicular, right click, perpendicular of that, it finds a perpendicular of that angle. And there's the third option, which is align with grid axes. Now we don't have a grid axis set up, so what I'll do instead is I will just select all those nodes and move them round. I'll just rotate them round a bit, let's say by 10 degrees. That would work. And this time I'm going to snap onto this beam here. You see I'm aligned with grid axes. So, and you can see this beam has gone in, snapped to that beam, parallel to that one, and likewise if I was to snap onto this one here, again it draws it in vertically. Now, this is not really what I want. select all those nodes. Let me just move these nodes back. We can split beams. As you can see, there's some splitting beams going on automatically there, and these splitting of beams can be, let's say, in number of equal parts, or at a distance, or at a percentage, or at existing nodes, for example. And likewise, if I delete those off, we can also split beams, and we can join them up. Now, under the 1D elements, see, we've got the split elements, but we can also join string of 1D elements. Now, what this will do is we'll join up elements which have the same property, which are orientated the same, and they have common nodes which are not in use otherwise, such as no point nodes, no beams connecting in, and so on. And so we now have back to just three elements with a number of additional nodes, which is where we want to start from. So let me just delete those off. Now, these beam numbers, we've now got a gap in our beam table, so I'm just going to tidy that up by using the manage data, and I'm just going to delete out my blank nodes and elements, and this will compress the model back again. Doesn't make any difference to the analysis, but can make the model that bit neater and easier to deal with. So this is my staircase, this is my first landing. Let me just shove that over there so we can see what's going on. Move and copy commands. Now there's a command which is like move and copy, which is called extrude. And if I just select that beam there, under sculpt, extrude selection, I'm going to copy this beam in the X direction, let's say 2 increments, 1 meter each time, and it copies it over. But if we click this button here to include beam elements along the extrusion, you see it copies that beam and joins the nodes up. Now, this is going to be a staircase. This is a bit flat at the moment, so what we want to do is adjust the slope on this. Now, we can use the move command on these nodes. Let's move that up by 0.5 meter. Let's move that one up by 1 meter, and it's okay. It's a little bit slow. So another quick method is one thing called the flex command. I select these 2 nodes which I want to move, but I also select this node over here, which is going to remain stationary. So this is going to be like a pivot point, and I right click on this node here, call that flex line of nodes, and I'm going to do a linear flex. So the node's going to be in a straight line. I'm going to flex it up in the direction by 1 meter, and the nodes are going to be spaced evenly. In this case, spaced evenly or spaced proportional to their original spacing doesn't make too much difference here. But you can see the end result is the same. Now, this flex command can be very useful for other tasks. I'm just create a series of nodes in there. And what I'm going to do is I'm going to select these nodes here, and I'm going to use the flex command. Let me pick that one there, for example. And if we have a linear flex, now note that this one is going to be moved by nothing, and the extreme nodes 9 and 17 are going to remain stationary as well, and everything else will be forced to move into a straight line. If we did a proportional move, then it's proportional to their original spacings. Similarly, we can force them into a circle, into an ellipse, into a parabola. Alternately, if I change this end node and force it to a linear vector, so they're all straight up and neat, and then flex that line. Let's say node 11, move that in the couple of meters in the Y direction. And so on. If it's circular, you of course just set a radius, and can be a very useful tool for creating complex geometries quickly. So, I have our staircase. Now, let me just put in the half landing. Use the previous commands. X direction, 1 increment, 1 meter, include beams. The extrude command in this is only an X, Y or Z direction, but if we create a axis set in the plane of the slope staircase, now this is a 1 in 2 slope, I could work out that angle and create this axis set. Alternatively, I can just select 3 nodes and use the tool to create user axes, which is this one here, and I just toggle through. Let me just toggle through the graphical options, and you see this is one. Green, y-axis up the slope, x across, z perpendicular. I'll call that slope. Let me just switch on display, so we can see we have a slope axis running up the slope. So what I can now do is I can pick this beam here and use the extrude command. And this time, rather than the global Cartesian, I use my slope axis. Goes to the Y, 2 increments, 1 meter, include beams, and you can see it creates a slope up front. Now, so we've got the overall geometry. Now, next need is support points. Now, support points, we can select nodes, and we can just modify these. And we can say these ones are going to be pinned. Alternatively, we can edit nodes. So let me double click on this node, and I can go and say I want this to be restrained in the Z direction, but note just above there is an axis set. This can be Z in the global direction, but we can say is that axis, it's actually going to be Z in the based on the slope axis, which means that if I look on elevation, this node will not move in that diagonal Z direction, but it will be able to move in the local X and Y. So that's a sloping support. Another option is rather than fully restraining it, we can set a support stiffness. And this then becomes a spring stiffness at a point, so it has some flexibility. So we've got section graphics. Oh no, we have beams, we have supports, we need sections now. And sections, we have catalogue sections and parametric. So the catalogues, if you look in the catalogues, there is quite a range of international catalogues. It defaults to British, but you can set whichever you prefer in your preferences. I'm going to take Chorus Advanced, and then this staircase I'm going to create parallel flange channel 275. If I switch on the display there, you see there is our sections. I'm going to create the second one, which let's say is a parametric channel, and I'm just going to set the dimensions this time. Let's say 150 by 75 by 10 mil all the way around. Now, this hasn't been used as yet, so what I'll do is I'll just go and plan, select elements, selection window, right to left, so it's a crossing window, and then modify those to say property 2. And you see these are now the smaller sections. Now, because these are channels, these are asymmetric, and as you can see, these ones are toes out, these ones are toes in. We want them all toes out to correct angles. Let me just go and select those ones there. And we could add in an orientation angle onto these. 180 degrees, so it would look right, but if you look at the element axes, you'll see that those beams are all actually upside down, which means the bending moments will be upside down. So this is not really a good approach. Instead, there is the flip command under the sculpt menu, and this literally flips them. It changes the node orientation, the node definitions. Now, to orientations, we see these channels on the slope are orientated wrong, so what we want to do is orientate those as well. Now, I don't know what the angle is for a 1 and 2 slope. What I want to do is make them toes down this slope, and then I want to orientate them on the slope itself. Now, you see node 7 there for this element. I'm just going to modify that beam, so the orientation node is node 7. So this node, that beam to that node, and you can see it's now aligned. And I'll quickly do that for that one as well. They have a basic structure. What we now need to do is put loads on. Now, loads, we can select multiple elements, and we can copy those beam numbers. If I go into my beam loads and just paste those in, and we can see there's the beams. Alternatively, let's grab those. Alternatively, we can select elements and right click and say create beam loads. Lowercase 2 minus 1, and there's the beams. Or if I open up the beam loads table, for more cunning, we can use the property references. Now, if you type something wrong into this beam list, you see what we can type, and down here you see property beams of a property number. So property beam 1, lowercase 3, and all those beams with that property are now loaded. Another useful technique, if I select those beams there, we can, rather than copy selection as list, we can save selection as list, and create a list there, which means we can then load cross members, also lowercase 3, and it then picks up that list of elements. You can also display that list. You can get results on that list, and so on. So that's 1D elements. Let's have a look at naught D elements. Now we have two types of naught D elements in GSA. We have ground springs and masses. Now masses are literally what we say there. They're just a weight. Mostly used in dynamic analyses, can also be used in general analysis for self-weight calculations. And if I set the default type to mass, it just puts a mass element on there which weighs that amount. The other one is the ground spring. And the ground spring is literally a spring which is maybe set to translation or maybe compression only. I would say it's compression only in the vertical direction, and has a stiffness of whatever it is in particular. We can then say this is going to be a ground spring, and we can position it at a nose. And so this will now have vertical downwards resistance, but not in any other direction. Next we have 2D elements. Now 2D elements, the axes are a little bit more complex than the 1D elements. First of all is the perpendicular to the elements. Now this is a warped element, so this is just warped for exact demonstrative purposes. They should be flat really, but the principle is you take the diagonals, two diagonals, and you can then work out the cross product of those to find the perpendicular. Once you have the local z-axis, you then need to find the local x and y. Now by default the elements are defined by the local axis, which means the local x is parallel to the first edge defined. Doesn't make too much difference to the analysis, unless of course you're using orthotropic materials, but it can make a difference to the results, especially for doing, say, concrete design. Where the reinforcement results are relative to the local axes. So generally what you want to do is set the elements to have a particular different axis set, such as the global axis, which is good for flat or horizontal elements. But if you're dealing with a wall, then you need, these don't really work, so you need to have different axis sets for different planes of 2D elements. So let's start up a new model. What I'm going to do is I'm just going to use the snap grid, which by default sets to 1 meter spacings, but what I'm going to do is defaults. I'm going to draw in quad 4. Snap to the grid sections. And then I'm going to draw a triangle. Now, the manual meshing trick is to draw large elements in and then split them down. Now if I pick this quad element, you see we have a number of 2D element operations we can do. This one is split quad elements, and note it's based on edges 1 and 3 and 2 and 4. Well, this is my first edge that I drew, so this is edge 1, and I'm going to split this one into 4. So we've got 4 pieces this way, 2 the other way. Let's make it 4 each way. Triangles have to be split slightly differently. So we have a separate split tri-elements, and triangles can be split into more triangles or they can be split into quad elements. Likewise, you can split quads into triangles. So what I'm doing the split is into triangles. And we have the mesh breakdown. Now, if this was a flat slab and we had these were our support points. At the support points, you're getting higher concentrations of load and moment and so on, and so you need to find a mesh or a refined mesh. So if I just pick this element there, and I refine that quad element at the corner. Now it's going to be 1, 2, 3, 4. So you can refine the mesh at a point, but that can be quite slow. So what we'll do instead is I've got those 4 points selected, and there's another command which is refine mesh at nodes, and that refines anything which is any mesh which is touching its quads or triangles to give you your sort of fine mesh and therefore the better analysis results at those points. Now I mentioned about axes, so I'll switch on my element axes. So these are all set to local at the moment, which means they're okay for most of the quads, but you see some of these triangles and so on, they're all a bit mixed up. So just need to set in the properties. There's a flat shell, it's a global axis. I'll just take that to the defaults, and you can see now all the local axes now line up. Now this is a manual mesh, which is okay for really regular shapes. What I'm going to do instead, and delete these out, is create an automatic mesh. So I'll just take these points here. What I'm going to do is I'm going to change from the analysis layer, where I've been working, to the design layer. Design layer is where you both do still design but also define meshes. Now we have some additional buttons up here now, and meshes are defined by lines, areas and regions. Now lines mark the edges of the slabs, and these also give the mesh density. So using control to do a multiple placement of these lines, and then once we've got a closed loop, we can then add an area. So lines, they say default to 6 segments, but what we want to do is use a step size. Which will be 1 meter centers, and the area then takes those lines and then assigns the element property. Now to do the mesh, let me select that area. I can right click and say add a region, and the region then additional settings such as the meshing style, its density, the type of element created, and some other options. Well, this means if we then go and generate this mesh, and flip back to the last layer, we see we've got a mesh of 2D points. Now if you wanted to avoid the middle of this, let me just delete that for the moment and go back to the design layer. What I'll do is I'll add in a new area there, and this area, area number 2, I'm going to change this to being a void, which means you then get the void across the middle, and I'm going to edit the region so that region will include area 2 as well. So if we switch back to the nice layer. If we remesh this slab, we can see we then get a void in the middle, which yeah, I mean, we might have to play around with some of these settings, maybe change the region definition from constant to a linear, and that can sometimes give, let's regenerate, better mesh. Yes, I think that's nicer. Okay, now with this also meshing, obviously that's created general mesh, but let me go back to the design layer here. Let's say we had a point in here which was going to be, say, a column coming down or so on. So I'm just going to add in a point. Let's say the point is, well, I'll snap a little less so we can see it. So that there's a node there. This node is node 10. If I add node 10 into the mesh, and then generate that mesh, you can see that the mesh is topologically tied to that nodal point. But if I right click and I might edit that node in the edit node properties, you can say instead that that node is going to be tied to the mesh. Now what this will do is it will create a tied interface between that node and the closest mesh elements, such that the node remains in the same place on the face of those 2D elements, so you can apply loads to it, but the mesh doesn't have to tie in like this. So if I just regenerate that mesh, we can see that that node is on the surface, but if I switch on tied interfaces, just rotate about that point. It's actually node display off mode. You can make out little red crosses associated with that element. So this node is now fixed onto the surface, and so you can apply a point load onto the mesh, and it's then distributed onto the 2D element accordingly. Right. It's about 50 minutes. I think it's best to leave it there and say, Nigel, do we have any questions?
Okay, excellent. Cheers, Peter. Yes, if everyone can, well, everyone who wants to ask a question, if you can now just type it in the questions box, Peter will endeavour to answer that. Give you a couple of seconds to jot it down. Okay, is there a fast way, Peter, to mesh a curved face, e.g. a cylinder?
Good question. Okay, yes, there is indeed. This is where the wonderful extrude command, well, a combination of the extrude and the flex command come into their own. Let me tidy that up. Let me just do a new service now. Right. Let me snap grid on. What I'm going to do is I am going to, so first of all, create a line of nodes. So what I'll do, if I create a, each way often is to, no. Let's put a node in there, which is away from the global center, and I am going to take that and I'm going to copy that around the global cylindrical. Let's say if it's 10 degrees, let's make it 30 degrees, a bit simpler. and 12 spaces. Yes. So we've got a series of nodes, and what we can then do is now we can extrude these nodes up. Now if you extrude the enclosed circle, there's a slight glitch. What we need to do instead is to extrude about half of it first of all, and if I extrude that selection in the Z direction, let's say 10 increments at 1 meter centers. Yes, it is. It's got confused. Into a quarter circle. And the last part, shame we can't do all of them at once, but it gets confused. So yes, you can quite. The curve surface obviously has to be segmented, but yes, it is quite quick.
Okay, next one. Does the mesh represent load-ins, or does it just add the surface?
It depends on how you define the what the 2D elements are. Now, if I go back to these elements here, now these elements here, yes, it's all down to the 2D property definition. Now, in this particular case, I define these 100mm steel plate. Okay, maybe let's say 100mm. Let's say 150 concrete. So yes, so in this case, these would represent solid surface elements, which we can then apply load to. But with GSA 8.6, there's now another type of 2D property, which is we call a load panel. And with these load panels, you essentially they take load and they spread load onto adjacent beams. So we need to have beams around all 3 or 4 sides, and it's then broken down into according to the pattern you choose. Now, because you've got to have panels on elements on each side, you can't just if I was to just draw oops, I should change that property. Now this is nope, modify that to property number 2, which is the load panel. This load panel won't work by itself. You need to have beams running around the outside, and then any load applied onto this load panel is then will then create UDL loads on those adjacent beams during the analysis automatically. So they're like miniature grid area loads, if you're familiar with those.
Okay. Right, we have a couple now. Just 1 second, Peter, as I have a look. Right, if a mesh contains a lot of elements out of shape ratios, so that they're fairly ill conditioned, I would imagine that means.
Yep.
GSA can refine them, but so how do you refine the mesh?
Okay, now let's take this one here. And in fact, I think there are some elements in here which are getting a touch unrefined. Let me contour them by their angles. And you can see, yes, there's this chap down here, which is he's beginning to look a bit coarse. Now, there are a number of ways that you can adjust this. I mean, one of them is to adjust, if it possibly, the step size in the adjacent lines. Sometimes you're going from a large to a small area. Changing that can help with things. You can go in and actually start dragging nodes around. Now in this particular case, I've just snapped the grid on and snapped the point, so I can use this drag tool and I can drag nodes about to improve angles. Note of course that if I remesh, this aspect will be lost. It'll be reset. If you create a manual mesh, or if you're in a real hurry, there is a trick. If I select that element there is the split quads down to triangles. Now, because obviously triangles by definition are much happier with sharp angles, this will take the largest angle and then draw a diagonal, and you'll then end up with a happier mesh elements. But I said, if we regenerate the mesh, you'll note that these triangle elements are not counted as part of the original mesh, and therefore you will end up with getting duplicate elements in there. So you can do it in emergency, but I wouldn't recommend it full time. Other options, is of course to adjust. Let me just go and delete that mesh. Change the layer. We can add in additional lines in here. Let's say there to there, and let's say there to perpendicular. So we now have additional. Now that, maybe I shouldn't have added the area. Let me just okay, and then another area. Note that you can't have a void touching the edge of an area. That doesn't work. So we've got, I'll just delete that void out. So we've got two areas, areas 3 and 4. 3 and 4. And if I remesh that, area 3 is not a single closed loop. Right. Oh, not the one. This might not work either, but let's try this. This might also throw an error. Let's see. Yep, partly overlapping. I'll just remove that out for a moment. You can add in additional lines and force the sort of control how the mesh goes locally. Yeah, that was badly done.
Okay.
It's
Right.
ongoing.
So
Yeah.
last question. So last question we have is just a little bit of advice required on how to mesh a flat slab, which I guess is what you've just done there, but specifically at column connections.
Yeah, column.
So where a column comes into the slab.
Yeah. So if I was to let me just delete this mesh a moment so we can see a bit better. So let's say we've got a column coming in at this point here. Now, at the column location, you need a sort of a finer mesh. So let me switch over to the design layer. I'll just tidy this up a moment. This node here, this is going to be a column, so I'm just going to extrude down. And what we want is a finer mesh over this point. So if I edit this node, under the mesh attributes, you can also increase the mesh density. Let's say over a range of 1 meter. Didn't much effect. But okay, with I suppose the elements are already similar, that sort of half meter size. But the moment you've got a full pin support there. Now, if I select this element, there is under the sculpt constraint operations, we can create a rigid column slab connection, and this can create rigid link at those points. Such that if I switch its contours off a minute and switch the nope. We can see that this creates a rigid link from that column to the connecting elements, and so that will then sort of deal with those localized, unrealistic peak moments directly over the column, and give you sort of better results. To actually analyze, but to look at results, let me just pin that, and I'm just going to whack some loading in. Let's just gravity load. And beam sections are defined, of course it is. Right. Properties undefined. Reanalyze that. Okay. Use standard material. So we have got a flat slab analyzed. We've got some deflections, which probably not very much. Yeah. And from the results you then get things like overall forces, so maximum, let's look on the plan view in a minute. Maximum, now note that these are linear or quad forces. 4 elements, so the contouring is not very smooth. If we use quad 8, you get a much smoother result. But these are the maximum and minimum moments, but you can also get the moments in particular directions. So this is the moments in the X direction, the moments in the Y direction. We can smooth those off a bit so we get slightly nicer contours. The torsional values and the Wood-Alma moments, primarily in the X, primarily in the Y direction. And there are also objective forces, stress calculations, and so on. But basically the results are from the,
Okay.
sort of the contours.
Yeah. Okay. If anything else is needed on that, I suppose we can pick up on that afterwards with the relevant people. Okay. We've overshot now by about 10 minutes, Peter. So I think we should draw this to a close now. So just to let you know, guys, that there will be another webinar. Can you show the?
Yep.
There will be another webinar in July. It's on measuring human-induced vibration. So essentially how GSA deals with footfall analysis and other types of vibration. So hopefully you can attend that. So thank you very much for attending. Thank you very much, Peter, for another useful presentation. So we'll leave it there for today. So goodbye, everybody.
Thank you very much. Goodbye.